Imagine you are mapping out a city, trying to group neighborhoods based on how crowded they are. Some are packed with people, while other areas are nearly empty. What if there was an algorithm that could automatically find these clusters without you telling it how many to look for? That's where DBScan comes in. Unlike traditional clustering methods, DBScan can detect noise, handle oddly shaped groups, and adapt to the real world data like magic. In this video, we will break it down step by step. Let's dive in. Before we begin, if you have not subscribed to my channel yet, please do subscribe to my channel and hit the thumbs up button. First, let's understand the core idea. DBScan stands for Density Based Spatial Clustering of Application with Noise. This groups data point based on density. Instead of assuming a fixed number of clusters like k-means, DBScan actually look for high density regions separated by areas of low density. Now let's talk about the two key parameters that make DBScan tick: epsilon and minimum points. First up, epsilon. Think of it as a search radius around a point. If 2 points are within this distance, they are considered neighbors. A small epsilon captures only very dense cluster, while a large might merge separate groups into one. So we pass this parameter as the distance. So if we take a larger distance, it will encapsulate larger groups into one. Choosing the right epsilon is crucial. It's the difference between finding meaningful patterns and ending up with a single giant cluster. Next, we have the minimum points. The minimum number of points required to form a dense region. If a point has at least minimum neighbors within epsilon distance, it becomes a core point, helping to grow a cluster. Now let us discuss what are the three types of points that it is forming. So the first is the core point. A core point is a point, say P, that has greater than minimum number of points within the epsilon radius. So we just saw what is minimum number of points, and we also saw what is the epsilon. So epsilon is the distance and minimum number of point is the neighbor points that will be taken into consideration. If the P has at least these many number of neighboring point, then P will be considered as a core point, and then we will discuss about other points which do not satisfy this condition. Okay, so let us understand this with an example. So for example, I consider this as my core point. Just assume that this is a core point. We do not know now, but now when we run the algorithm will check within the epsilon distance. Say this is the epsilon distance and this is the epsilon value, and if I form a radius, so it will form a circle like this, and minimum number of points that we are given as a parameter are 5, and we have the epsilon e as the distance. So it is encapsulating 6 points, which is greater than m. So 6 is greater than our minimum number of points. So that means this particular point is a core point. So if we count, so it is 1, 2, 3, 4, 5 and 6. So you see that this is satisfying the condition that we have seen for the core point. That means this particular point is a core point. Now let us see what are border points. So a border point are the point which does not have the minimum number of points within epsilon. So it does not have the minimum number of points within the epsilon radius, but there is a condition to border points. It has at least one core point in the epsilon radius or the epsilon distance. Okay, so let us see with an example. Let's assume the model is evaluating this particular point and the epsilon distance is this much. So this is the parameter which has already been passed, and I draw a radius with this, and it is something like this, and it is forming a circle. So we will count the number of points. So 1, 2, 3 and 4. 4 points are the neighboring points which are encapsulated within the epsilon distance. But if the m hyperparameter is 5, which is greater than m is greater than the neighboring points that it is encapsulating. So this condition does not satisfy for the core point. So this is not a core point, but this is a border point. Okay, so this is how the model will evaluate a border point. Now coming to the next point, which is the noise. So our noise is nothing but a point which is neither a core point nor a border point. So for example, this is the point for which the model is assessing, and this is the epsilon, and it encapsulates this much, and it is encapsulating the neighboring point. But you see these points are left out, and these points are not having any bridge between other points as well. So that means these points are neither a border point nor a core point. So these are considered as noise. Okay, so let's summarize what we have learned so far. So how does this algorithm works? So first of all, we will be passing two parameters. One is the epsilon, the radius, and we will also pass the number of points. Okay, so these are the two hyperparameters we'll pass for dbScan. Now dbScan will evaluate the counts of the neighboring points. So if the counts is more than the minimum point that we have passed, then it will mark it as a core point. And if the point count is less than the minimum point, then it will be marked as non-core point. Now coming to the next step. So in the non-core point, if at least one point is a core point, then it will mark it as a border point. And if it is neither a core point nor a border point, then it will be marked as a noise. Now let us quickly look at some advantages of dbScan. The first and foremost advantage is that you don't have to select the k hyperparameter like in k-means clustering. And the second is it can form non-spatial clusters, unlike the k-means clustering where you need to have the spatial clusters. So it works very well in non-spatial clusters also. And it is not sensitive to outliers, which is the most important advantage, so that you can identify the outliers using the dbScan. And fourth, it requires only two hyperparameters that we already discussed. And fifth is that it can handle clusters with different shapes and sizes. Okay, so let's discuss some limitations also. So two major limitations are, it is quite sometimes difficult to tune the hyperparameter, both epsilon as well as the minimum points, and it is an offline model. Offline model means that it cannot be saved as a pickle file or as an artifact. So but enough of theory, let's see dbScan in action. Watch as we plot points on a map and let dbScan dynamically find the clusters. So we will pass two hyperparameters, that epsilon as 1 and minimum point as 4. First, let's just try with this. You see that how these points are forming the bridge with other points. So each of the red means this is only one cluster. So each point is being assessed with the epsilon distance with its neighboring points, and if that point satisfies the minimum point criteria within that epsilon range, that point is also considered within the same cluster. And this is how one core point forms a bridge with other core point. So one cluster is over, but this cluster is not bridging with this cluster. That means This is a separate cluster, this is a separate cluster. See how beautifully it can form clusters without any spatial shape. And our clustering of dbScan is done. But I wanted to show you guys one more thing, very important concept. Here, if you increase the epsilon distance, what will happen is the number of clusters that are formed will be lesser. So for example, if I increase it to 1.98 and then I execute it, you see most of the points are being forming only one red cluster. So if you increase epsilon, the number of clusters formed will be less. And it's going to take some time. Let's restart it. And let's keep the epsilon constant and we increase the minimum points. So if I increase it to 6, so if again you increase the minimum number of points, what will happen is the number of clusters is going to be lesser. So it's the vice versa. So you see, whichever point is not colored is a noise, which is neither a core point nor a border point. Let's restart it, and one more time let's try with the minimum point as 2. So we reduce the minimum point this time and then we execute it. So we see there is more number of clusters. Earlier there were lesser number of clusters with minimum point as high, and now I have reduced the minimum point as 2, so there will be more number of clusters. Now let's get hands-on and implement dbScan in Python. So we will use scikit-learn to cluster our data in just a few lines of code. So we will load our Titanic dataset and apply dbScan to visualize the results, and even tweak the parameters to see how it affects the clustering. By the end, you will have a solid grasp of how to use dbScan for your own projects. So I'll just execute these importing of packages, loading of data, and I will drop any values if any. Now we are going to take only two parameters or two variables, which is age and fair. So let's just first plot a scatter plot and see how it looks, and then we are going to just see that we create a new data frame which just contains age and fair, so that it will be easier for us to pass it to dbScan. Then we will import the dbScan library using the scikit-learn.cluster, and I'll just execute it. And now I'm going to call this dbScan class, and we will pass some hyperparameter in the epsilon and minimum samples. So this is how we are going to invoke this class dbScan. We pass hyperparameter, say 10 for now, and minimum samples as 2, and we will do dot fit on the data frame sliced that we have already done. And so let's just execute the labels, and we see that there are n number of labels, with -1 being the noise. And if I see total number of cluster it has formed is 11, and if I plot this with the cluster, you see for each color a new cluster is forming. So you can play around with this, you can change epsilon and minimum samples and you will get a different cluster. And there you have it, dbScan, an algorithm that doesn't just cluster data but actually understands it. Unlike traditional methods, it adapts, finds patterns, and even filters out noise, making it one of the most powerful tools in unsupervised learning. We explored its concept, broke down how epsilon and minimum points shape the cluster, saw it in action with an interactive visualization, and implemented it in Python. Now it's your turn. Experiment with different data sets, tweak the parameters, and see what inside dbScan can uncover for you. Got questions? Want more breakdowns like this? Drop a comment below. I'd love to hear your thoughts. And if you found this useful, don't forget to hit that like button, subscribe, and turn on notification so you never miss a deep dive into machine learning. Thanks for watching. Until next time, keep exploring, keep coding, and keep pushing the limits of AI. Bye bye.